Okay, this is Dr. Williamson. Some students asked me to solve this problem for them and to go through this. So we'll go ahead and do that. It says the rate law for 2NO plus O2, that's O subscript 2, goes to 2NO2 is equal to rate equals K NO to the power of 2 times O2. O subscript 2. Remember, the software program I'm using doesn't let me do superscripts and subscripts very conveniently. In addition to the mechanism found in the text, the following mechanisms have been proposed. Mechanism 1 is this. Mechanism 2 is this two-step mechanism. That's a fast reaction and a slow reaction. Mechanism 3 is a fast reaction and a slow reaction. Which of these mechanisms is consistent with the rate law? Which of these mechanisms is most reasonable and why? So let's take a look. Our experimentally observed rate law is this. So this is the one that we take to be the truth. So let's take a look at the rate law that we get from this elementary step. We get the rate from that, from mechanism 1. Oops, that was a letter Z. Rate from mechanism 1 is equal to K times NO squared O2. And that is consistent with the experimentally observed rate law. So and remember, when it comes to elementary steps, the powers are used for the exponents. Over here for this overall reaction, this number 2 here coincidentally happens to be the same as this, but for overall reactions, you don't automatically use the coefficients as the powers. You need to know that difference. But for elementary steps, you do. And for this proposed mechanism, the experimentally observed rate law here is consistent with the rate law for the mechanism. So that does seem to work. What about the rate law for mechanism number 2? I'm going to do that in a different color. Let's use blue. And I'll do it over here on this side. Rate law for this mechanism, whenever we have a fast reaction followed by a slow reaction, it usually means the fast reaction ends up going into equilibrium, because the slow reaction makes the fast reaction that precedes it bog down, and it ends up going into equilibrium. So the rate of this mechanism comes from the slow reaction. So we're going to write the rate from mechanism number 2 is going to be equal to the rate constant from step 2, right? This is step 1, step 2, times concentration of N2 O2 times the concentration of O2. Okay, that was a little bit messy. O2, square brackets. Notice here we have N2O2 as an intermediate. We want to get rid of the intermediate if we can. And we're able to because this fast step is in equilibrium. That means the forward rate and the reverse rates are equal. So the forward rate of the first step is equal to the reverse rate of the first step. So I can write K1, I'm talking about the first step, not mechanism one here, times, times NO squared is equal to K backwards times N2 O2. So I can algebraically rearrange N2 O2 is the same thing as K forwards over K backwards times NO squared. I'm now going to take this stuff and substitute it into here. That's going to give me the rate from mechanism 2 is equal to, and I'm going to leave the K2 in the front. Okay. Let me move this down a little bit. It's equal to K2. Let me put this stuff in there. K1, K of the backward step, NO squared, and O2. Right. If I do that, let's see if I did that right. And if I did that, wait a minute, let me take a look here. If I did that, that also looks consistent with this mechanism, or that also looks consistent with this, right? That looks consistent too. That interesting. Okay. Let's take a look. Let's go to this one here. Let's do that in a different color. Let's try, how about, well, maybe green's a nice color. R3. We have a fast step followed by a slow step. This sequentially happens before this. This is so slow that it bogs this down into equilibrium. So the rate law for the mechanism comes from the slow step. So that's going to be K2 times N2. And we're going to have here O2 squared. This does not look like this, but again, we have an intermediate. We want to get rid of that intermediate by taking a look at the reaction that precedes it that happens to be in equilibrium. And if it's in equilibrium, that means the forward reaction rate is equal to the reverse reaction rate. Forward's reaction rate for that step is going to be K1. This K1 is a different numerical value than that one, but okay. Times NO. And that's going to be squared is equal to K backwards 1 N2 O2. We're going to solve for N2, so we can substitute that out. So we're going to end up with N2 concentration. It's going to be equal to K1, K backwards 1 times NO squared over O2. We're now going to take this stuff, substitute it into there, and we're going to get R3, 2, 3, is equal to K2 times K1, K backwards 1 times NO squared over O2 times O2 squared. And this will cancel with that squared. And that will give us, going back to green here, K2, K1, K backwards 1, and O squared, O2, right? And lo and behold, this and this are all consistent with that, unless I made some mistake, right? In the sense that they're all consistent if right, if K is numerically equal to K2 times K1 over K backwards 1. If these numbers numerically end up being the same value as K, then it's the same. So which of these mechanisms is consistent with the rate law? In terms of, they all seem to be, right? Okay, if I do that, so they all seem to be. Which of the mechanisms is the most reasonable? It's going to be the one that is the least molecular. In other words, it involves the least number of molecules colliding. Right? This one here involves 3 molecules colliding, 2 NOs and then O2. This one involves 2 of these decomposing, and then 2 of these colliding. So each step here, this is unimolecular, or actually it's decomposition. So 2 of these colliding with each other, going this way. I've got 2 NOs, so that's bimolecular. And I got N2O2 colliding with O2. That's also bimolecular. Okay. This is 2 NOs and an O2. That's what? Trimolecular, or does the book call it ter? I forget. Okay, anyway, that's 3. Okay. That's more complicated. 3 colliding at the same time is much less likely than 2 colliding, and then afterwards 2 colliding after that. This one here, this step is bimolecular. And then this step is 1 molecule and then 2 more. So this is trimolecular. So the ones that's most reasonable is going to be this one, because bimolecular in each step is much more likely. That's 2 molecules colliding with each other, much more likely than 3 separate molecules all colliding at the same time at the same orientation. So all of these seem to have their rate law match the rate law of this, but the most reasonable one is mechanism number 2, because bimolecular is much more likely than any trimolecular, or does the book say termolecular? I forget, or maybe whatever. But you guys get the idea. Okay. So anyway, that's how you do that one. Okay, then I hope that helps.